Today we're going to be starting a conversation about railroads. This will be a 2-day session before we're done on that. And then next week we'll be hopefully doing some traffic calming. So I'm hoping to get together some traffic calming stuff from a fellow who works for a consulting firm down in Indianapolis. So that's what's coming up ahead. So today we're going to talk about railroad terminology and what some of the components are of that. We've already gone through roads, right, and looked at how roads are built, and we've talked about drainage, we've talked about the pavements, and we've talked about somewhat about the vehicles of it and what we can expect for turning. We've talked about the geometric design pieces of that, right? So we're going to try to relate that now and switch to railroads and kind of a short talk about the railroad piece of it. And exactly similar components, right? It is a railroad, and so it does share a lot of things with roads that we've already learned, and we're just going to adapt it and basically highlight what's different when you're looking at a railroad versus a highway through that. The first thing is highways are owned by the public. I guess there's some privately owned roads. There's very few, but there's some privately owned ones. All of the major roads, all the kind that we've been looking at, really are public roads. And that's the huge difference, is that there are very few publicly owned railroads in the United States. That is just not the way it was done here, right? It didn't start that way, and it's still not that way. And a lot of other countries have nationalized their railroads, or they started it nationalized, right? So some of our friends from China, their railroads are all nationalized. They're owned by the government. And so they can easily make a decision about how they're going to run their railroads and what kind of equipment and stuff they're going to use. Here, our railroads are privately owned, right? So Amtrak, which is our only government railroad operating right now with full service, and which is all passenger traffic, they only own one rail line in the entire U.S., which is the Northeast Corridor, going from Washington, D.C. to Boston. Right, okay. They may own a little bit of track here and there elsewhere, but as far as going miles between cities, that's the only rail line that Amtrak owns. And so on that, they have high-speed service, fairly high speed for the U.S. at least, 150 miles an hour, which other countries would laugh at, but that's what we've got. And it is good service, and it runs frequently and it runs fast because they own that line and they can make all the decisions about it. Every other passenger service we have is operating on privately owned railroads. And that's just how these were formed, right? So in the late 1700s, I guess the first one started, and mostly through the mid 1800s was when they really took off. States and territories would grant free land to a railroad if the railroad would build it. And they would grant, typically it's 100 feet wide right of way. You could get a 100-foot wide swath if you build a railroad on it. And that way, no public money was used to develop railroads and settle the West eventually, because roads were crap back then. They were really terrible, just all mud holes and just nasty. If you wanted to haul anything or get anywhere, you took a railroad, right? There were really no public roads until about 1910. No roads that were passable. It wasn't until about 1920, 25 you could get really across the state on a road and not taking a railroad for that. So this is the history piece. Sorry. These railroads were all privately owned and privately developed, and that was the big money back in the 1800s. You had railroad barons up and through probably 1910, 1920. You'd have these railroad barons who'd made a ton of money because they got free land and built the railroad, which a railroad is really expensive, right? I read once that as far as any business, it is the most capital intensive business there is, because you're literally building, think about it's actually more expensive than to build a road. Building a railroad is more expensive than a two-lane road, at least a two-lane road. For there, all that money you spend up front, and then you hope you haul enough people or goods to make that money back, right? And it worked, right? Let me look at this network map of the railroads through the United States. These are what's left. There used to be more. We've relinquished a number of railroads, right-of-ways, across the country, mostly because the competition starting after World War II with the cars, railroad freight traffic and passenger traffic has plummeted in the 1950s with air travel. And so that took away a lot of the cash and a lot of the money from the railroads. Railroads now, ever since 1971, was it? I think maybe early 72 was the last uh, passenger trains run by these private railroads. Before that, they all had competing passenger services, and it was a big competition, right? And they had like the Super Chief, which was Union Pacific going from Chicago to Los Angeles. You had the Penn Central line, which ran through Fort Wayne and Valparaiso and had the direct connection between New York and Chicago. You had New York Central, which ran the Lakeshore Limited, which ran up through past Albany and then followed the lakes, both Lake Erie and Lake Michigan, until it gets to Chicago. So those were in direct competition with the Penn Central line, and it was a big eastern competition. In the west, it was the Santa Fe versus Union Pacific, right? You had the Super Chief versus the Union Pacific trains running to LA. So that's a little bit of the history piece of it, right? So what we're left with now are all the bigger railroads. They're called Class 1 railroads. And so Norfolk Southern, Union Pacific, CSX, Canadian National, which is obviously based in Canada, but has a fair bit of track through northern, the northern U.S., and particularly it goes right through Valpo, their main line. That comes out of Chicago, it goes to Detroit, it runs right through Valparaiso. So you can, if you ever go up the north side, it's right next to the Canadian National line. Canadian Pacific also has some rail lines in the U.S. And I should say these Class 1s exist in both countries, both Canada and the U.S. Kansas City Southern is probably the smallest of the Class 1s, and then Burlington Northern, Santa Fe. All right, so these, starting in 1980s and really picked up steam in the 90s, there was a lot of consolidations in railroad companies, right? And some went out of business completely. So the Burlington Northern and the Santa Fe combined, and it's now BNSF, right? Santa Fe used to be mostly a Southern tier down here in the States, and the Burlington Northern had the Great Northern Line, which was the original. There was a Burlington Railroad, and then there was a Great Northern. They combined and formed Burlington Northern. Then they combined with Santa Fe, and so it's the BNSF now. They had this northern transcontinental route, right? The original transcontinental route went right through here, right past Salt Lake City and Promontory, Utah. And that's this red line. And that was Union Pacific. And then they connected up with Central Pacific. And then there was Southern Pacific down here in this part of California. All of those have since been gobbled up by other railroads. I think Union Pacific ended up buying Central and Southern Pacific. Not positive. I don't remember which one Southern Pacific ended up with. But anyway, there was a lot of consolidations. Mostly in the 90s, it seemed like, and then still some in the early 2000s through that. So these are the big ones that are left. There's 7 Class 1 railroads in the U.S. And that's by size and by volume of goods. That's how they separate a Class 1 railroad versus the others. Everything else is called a short line, and that's exactly what it means. Is they're short, and so they may be 200 or 300 miles long, and they just connect on to one of these Class 1s, which go usually transcontinental through that. Now, there is a major division between the eastern and the western railroads. The western ones are the UP, Kansas City Southern, BNSF, all run out here in the west. Norfolk Southern, CSX are in the east, are the main ones here in the east. You can see the by color here through that. Now, Kansas City Southern kind of mixes in the middle here, and it is based out of Kansas City, Missouri, and St. Louis areas. So they're a little stronger in those areas through that. Now, they all interchange traffic. You don't have to, your freight car, if you're hauling freight or if you're getting a container shipment from somewhere, it'll mix and match to some degree. All right, especially if you're on the East Coast or over here in the eastern side of the U.S., you have a container coming from the port in Los Angeles. It'll start out on Union Pacific and it'll end up on something else, as it comes to your direction through there. So that's just a little background on what the railroads are, and it makes it a really interesting thing is that because they're privately owned, they make their own standards, and the federal government oversees them. It's a little bit like how the federal government does airplanes now, airports. in airlines is an airline can make its own rules, but the FAA has to approve those rules and say, okay, yeah, that sounds safe. You can do that. It was the same thing with the railroads. There are still federal railroad inspectors who inspect track and make sure the railroads are maintaining track, because it started back when there was a high volume of passenger traffic, but they had to make sure to ensure the safety of the public, they would check that out. Now they also do it to make sure there's no chemical spills or train wrecks and so forth. So they will, federal railroad inspectors will come out and inspect the rail lines, but they're owned by these railroads, and their standards are set by those railroads. And so this is what the if you get hired and work for a railroad, you can ask for, you can find it online, or they'll send it to you, what their design standards are. And so we used to do some work with Norfolk Southern, so they sent us their design standards. And it can be, they're not a lot different, but there's some definite differences you'll notice between the different railroads, how they like to do things, right? And it's their preference. We also did some work for the South Shore line, which is a passenger, commuter passenger rail line, but also hauls freight for that. So the South Shore has very specific standards based off of the size of their passenger cars. Right? They have, I think it's 80 or 88 feet long passenger cars, which is a little bit odd versus what other passenger railroads use. And so for curves and so forth, you've got to make sure their type of railroad car can go around those curves fine. And they're electrified, which is an unusual thing in the U.S. There's not the Northeast corridor is electrified, and that's really it in the U.S. and the South Shore. There used to be, Illinois Central coming out of the commuter lines in Metro. Some of those are electrified coming out of Chicago, right? So that's shorter ones. There used to be one of the northern transcontinental one, the Milwaukee Road, was electrified all the way to the West Coast, coming across the northern tier of the U.S. But they abandoned all that in the 1980s. That road doesn't even exist anymore. You can pull up the track and everything. So, but that had been one of the only, probably was the only long distance electrified rail line in the U.S. For that. So it's kind of weird compared to the rest of the world for it. So everybody's got their own standards. There is a standards agency. This is ARIMA, which would be it's the railroad equivalent of AASHTO. And so ARIMA, the Railway Engineer and Maintenance of Way Association, they write standards that we have. The books are back in Senior Design if you want to go look for them. They're right there. So you can go back and check those out. And that's what you can use, give you a really good idea about how to design stuff. And it's a good start. And then, like, say, Norfolk Southern has their own specifications, which you can pick up or download. And you can see, well, they probably base everything the same as ARIMA, but then they have some adjustments, things they like than others do. How they signal, and if you get into that kind of stuff, that's different versus each railroad company does their signaling a little bit differently. Yeah, generally the track is all pretty much the same for sometimes what their maximum curvature or grades may be adjusted based on the company for that. So that's just to give you a rough idea. There is there is. This ARIMA manual is kind of like the Green Book, but it's even less stringent, maybe you could say, than the Green Book is for highway work, because what really counts is these individual railroad specifications from each company for that. And if you get hired by a railroad company, you're going to follow their specs. They'll send you their specs, and you'll follow it. All right. So here's a general typical track layout, and this is what it would look like in a typical section. So we've seen typical sections before with the roads, and this is the railroad version of that typical section. You can see here's our little rails. All right. For this is our gauge. We call this, the gauge is from the inside edge of the rail to the other inside edge of the rail. That's our gauge. Here's the size of the rail. This is 115 pounds per yard rail. And so every 3 feet of this rail weighs 115 pounds. I think it's every 3 feet. Or is it per pound? Or per foot. Well, anyway, it's a 150 pound rail. And that's how in highways, we would say, I need 6 inches of pavement, or I need 8 inches of concrete. right? How deep is my road, which is based off of how heavy are my vehicles and how much traffic do I expect. The railroad rail is set up the same way, but they list it by weight per unit distance, right? I think it's per yard. But it's so a stronger rail would have a higher number, right? So it used to be they were using 80-pound rail or something pretty light, and then 115-pound rail came in, and then as the rail cars and the locomotives got heavier, they would use heavier and heavier rail, right? I think there's 136 and 141 pounds rails now in use for this. This was a 115-pound rail. This was a South Shore design, and so their trains are not as heavy. And mostly commuter traffic. The freight traffic, even they don't. It's not as heavy as the Class 1 railroads, right? No, for that. So they're using 150-pound rails, and that's what we use for this project, right? So that's the rail. Down below it is we call it a sleeper, which is the tie, the railroad tie. It's usually a piece of wood, but it can also be concrete, can be steel. Sometimes you do direct fixation. If you do subway design, you'll actually just bolt the rail right to the floor of the subway system, right through there. Sometimes you form like a little, I don't know what you'd call it, ledge that you set the rail on top of and bolt that to that. But still, you could bolt directly to concrete slab. Usually, it's a wood tie, and that's by probably 80% of the ties in use are wood ties. A really high traffic route is going to use a concrete tie now, and it's become pretty popular just because they don't rot and they don't degrade, and they're stronger for that. Now they have some downsides too, but you may see some pictures of a really high traffic rail line, and they'll be using concrete sleepers, and that's seems to be more popular out west, I would say. Maybe because there's less wood out there. I don't know, or how that choice is made, what they do. Below that is ballast. And so this is the South Shore design. You have a minimum of 8 inches of ballast below the sleeper and below the tie through that, right? A larger, heavier loaded railroad is going to want more ballast underneath their tie because that's what's distributing the load, right? We talked before in the highway piece is, how are we, let me turn on my pen here. Let's see if the pen works. Oh, this isn't going to work at all because I mapped the pen to the other screen, which is a dumbo move. I can get it back here. Just give me a second. I'm sure you guys have anything better to do except here to wait and watch me fool around with my settings for the stupid little tablet that you probably don't even like anyway. Mapping. Map to that screen. Monitor 2. Got it. All right, now the pen's back. There it is. All right, so just like in roads, we're transferring the load off of the road. Remember, we had, if the road was looking like this, it still does that. When I'm not in present mode, it doesn't do those little jags like that. So who knows why. Here's my tire, right? And we were distributing the load out from the tire. Oh, that thing is nuts. There we go. So we're distributing load out from the tire. And the railroad is the same thing, right? We're distributing this load. It goes into the sleeper. This whole sleeper will move, right? This whole tie is going to move with the rail. And so it is all transferring load out. It can. It bends a little too. You'll see that as a heavy train goes by. But that's transferring the load. So that goes through the ballast. And we slope this out, to keep it stable, but also it helps with that transfer of load going through the ballast. Now the ballast is, it's roughly a 2-inch, I would say, aggregate, a 2-inch top size aggregate, and it's fairly clean. Well, they want it to be clean, and it usually stays clean for a while at least. It has a lot of voids in it, and so unlike highways, we have to worry about how to get the water off of the highway, right? Or is it going over here to the ditch? That thing drives me nuts when it does that. In a railroad, it's pretty cool, right? The water goes right down through the aggregate, right? It doesn't. It's super well drained. It is really well drained. Now, when it hits this layer down here, we were building a brand new railroad bed, and so we had this. We can get some this compacted subballast, and we slope it so that if the water comes through the main ballast, it'll follow this out and hit our ditch, right, and come through. Just like before, we don't really want this saturated. Well, we definitely don't want all the subgrade saturated. So if we can move the water to the side, we will, right? And so we'll slope the subgrade have a slope on it until it drains into the ditch. But when rain falls right above the railroad tracks, it's just going to go right through that ballast until it hits that slope subgrade and hopefully follow it off and off to the edge, to the side. So this is our comparison to how we did things with roads. This is the railroad version of that, and how we get our water off, how we transfer load, what the typical section looks like through there. And you might say, hey, there's definitely some interesting things. There's some good correlations from what we learned. Here's our profile grade point, which is at the center line of the tracks and right at the top of rail. And so that's our profile grade point. So on your plans, we show a profile grade line just like we do in road plans. And this is what the contractor knows to build it to. That's the profile grade line right through there. Here's our center line. That's our alignment line. That'd be the horizontal alignment for it. So that's, again, very similar to what we've got before. Now, we don't have to worry at all on railroads about the clear zone issues, and having a soft landing for cars that leave the road, right? If a train leaves the tracks, there's no soft landing. We actually do build bridge supports in a certain way to reduce the chance that the train will rip the whole bridge down. But other than that, yeah, you can use a 2-to-1 slope for railroads because, it's, they don't leave the tracks very often, and if they did, there's a whole lot of worse things that are happening than we have to worry about the clear zone, right? So that's definitely a big difference than we had with cars. Whoa, jump too far. All right, so let's look at the rail. Let's start there, and that's the first thing that's taking the load. This is the standard. This is from the ARIMA manual. This is what a rail design looks like, right? And there's two different kinds here, and they're a little bit different for that. And like we just said, it is pounds per yard. Yeah, I remembered right. So this is how many pounds per yard this steel rail weighs, right? So 115 pound one is a little bit lower duty, and 141 pound is the new mainline, super heavy, I can handle anything you can throw at me rail out there, right? For there. And that's what we're using it for. Heavier loadings, higher volumes, higher speeds, and sharp curves and higher grades, right? It can resist more by itself, and it's not quite an I-beam, right? You guys have had structural design, or you're in it now, or steel design, and you're probably sick of it, but it's, you can almost look at it a bit like a steel beam, right? Or a girder, especially like an I-beam, right? So we've got a really large is this the flange? Anyway, we've got this is the really large flange. This would be your other flange up here. Well, we've molded it into a denser shape, the head of the rail, and then here's the web, right? Just like you would have a girder. So this is your structural strength. This has structural stiffness in it in this direction, right? Very little in this direction. Right, it doesn't, if you're looking at the moment of inertia, it's got a lot of resistance to bending in the vertical direction, not that much in the horizontal, some from the plate here, right, on the rail. But there's another reason we have this shape on the rail, but we'll get to that later, right? So you can see as you get a heavier rail, the head of the rail is larger, so there's more material there. This is a little bit larger. There's more material there, right? And so that's giving it some extra strength. It's also taller, though. So it's definitely taller. This is 7 and some, I can't hardly read it, 7 and something 16th inches. And this one over here is 6 and something inches. And so that's, about a half-inch difference probably. Through maybe 3/4, that's given it even more structural strength, right? Resistance to flexing in the vertical direction, right? And so if you shoot back over here, I kept that stuff. Our profile grade is to the top of rail on the center line. But you can see if you use a different size of rail, now my profile grade lines up with this line versus down here. So sometimes if you replace the rail, you actually change your profile a little bit, right? You're actually putting a deeper pavement in. That's what you're doing effectively. Through that. So that's rail. This is, and there's different materials, right? So we've got standard, medium carbon rail. You can harden the head on the rail, and we'll talk about that here in a second. And there's fully heat treated, which is a heavily resistant one and even stiffer, right? So you're changing the Young's modulus, or the elastic modulus of the steel through that. And this is what it looks like. This is how you know what rail you've got. So this is a 133-pound rail. It meets the ARIMA specifications RE. It's head hardened, so only the head of the rail is hardened. All right, through there, it was vacuum treated. It was made by NKK, and this is when it was built in 1996 and 3. So you can walk up to rail and you can check it, and you know exactly what you've got, and that is handy. It would be nice if our pavement, if you walked up to it and it was stamped on it, it was 6 inches thick and it had 1.5 inches of surface and 3 inches of intermediate. And so, you know, that would be nice instead of having to get out a core drill every time you want to know what pavement you've got. All right, you just walk up to this and you know, that's 133 and I know it's head hardened and okay, off you go. Right, and here's the heat number, stamped heat number on it. So you can even back check that if you wanted to. All right, so that's rail. There's these 3 hardnesses, right? So you've got the standard. So this is our Brunel hardness. I don't know if you guys covered that in materials class back when you were sophomores, but this is, you know, the higher the number, the harder the rail is. And so you can get up into a higher class rail. So obviously a heavier rail, a harder rail, fully heat treated rail is the better stuff, right? That's going to be the stuff if you've got a really busy active rail line with a lot of heavy weights, then you're going to want that, right? Well, how much does a rail car weigh? That's a good question, right? We're talking about making a stronger rail for that. What's the load on a car? All right, so our standard load right now is for free interchange, which means you can move your freight cars on and off pretty much any freight rail line in North America. The free interchange weight of a rail car is 263,000 pounds, right? The class 1s are running 286,000 pounds. Why so heavy? Because you can make more money if you can have a heavy rail car, a single car that holds more stuff, right? So you can, that's why. All right, so that's this 286,000 one. That's the standard one. A lot of times, if you're parked near the tracks when a train goes by in Valpo, there, you can read right on the side. They paint it right on the side of the cars in little white letters what the gross weight is, and you're going to see a bunch right around here, around the 286,000 pound line. And that's why this is our standard load. And that's kind of the class 1s just got together and decided, yeah, that's good. All right. The problem is if you get much heavier than that, you deform the rail too easily. So this one's really hard to use. We're trying to get heavier, but this is about the limit of what can economically be hauled now without finding some new, even harder rail or even bigger rail than you've got. For that. And the hardness is going to be an issue here. I'll show you in a second why. And that comes down to 36 tons per axle on that, right? So what's a truck? What's a Indiana Design View, IDV? Right? What is the official legal weight of a truck, 18-wheeler semi, in the United States? Anybody remember? Right, 80,000 pounds. 80,000 pounds is the maximum weight of a truck in the U.S. And how much they have per axle, that varies somewhat. But like the trailer axles, per axle, you can often get, well, per tandem, you can often get around 32,000 pounds. So I guess it's 16,000 pounds per axle, right? So this is way heavier than what truck traffic is doing. Right, and that's why railroads are still in business, is because by hauling so much more in a single car, they're more efficient. That's how they make their money. That's what's the things they can haul more efficiently, which are bulk items, are things going a long distance. That's where they make their money. That's what they like. That's what they want. So it can be low value stuff, but if it's a lot of it and it's going far, that's where the railroads are making money. And so hauling heavy stuff like coal or aggregates or automobiles, even, if you're hauling far enough, then that's where the railroads become cheaper, and that's why they're still in business generally. Now hauling passengers, this is transit, right up here. And this is like an Amtrak car, is I guess 200,000 pounds. This is like subway cars, light rail transit. That's like street cars and trolleys and stuff right through there. Probably the South Shore line somewhere in the middle here. It's probably somewhere maybe closer to 120. Those rail cars are more massive than you would think, and on purpose. And they are also super expensive, right? It costs more than $1 million for one of those South Shore cars for that. So that's, pretty big investment for it, right? But this freight traffic is super heavy, right? And it's kind of amazing that 263,000 pounds, right? Divide that by 80. That's how many semi trucks would fit on one rail car by weight. For that. Well, what the hardness comes down to is here's a wheel, a car wheel on a railroad on the rail, right? And they are that shape, right? So you've got it's conical shaped through here, but let's say it's circle. And where it intersects with the rail, it's a small area. It's like a half square inch, right? So you're getting, back it up here, you're getting 36 tons on an axle. So that'd be 18 tons on each side, each wheel. 18 tons is on an area that's a half square inch, right? That is why this has become the limit, is because that much pressure even on steel, for that will deform the rail eventually, and that's why they do hardening on the rail head, is so that when the train's rolling, it's not a problem, but when it stops, all that weight sitting there for a long time will deform the top of the rail, and you have to come by and reprofile the tops of these rails at times because they get too bumpy from that traffic. And that's what's really limiting rail cars getting any heavier than they are. I guess you could add axles to it and something like that. Locomotives have 6 axles usually now. I guess rail cars could go from 4 on each end to 3 on each end, go 6. So that's why hardness is important on the rail, and it's because of this, right? We have such a small contact area, and that 286,000 pounds is pretty much at the limit of what can economically be built and maintained and so forth right now. This is what it looks like a little bit from the side. There's an inside flange, obviously, on the rail car wheels. I think you probably knew that. Forward there, if this is built right and it's straight and true, and this wheel on your car is actually a little bit conical, right? It's not flat here straight across. It's got a little bit of a slant to it, and if everything's right, if this gauge is exactly right and everything's built well, this flange will never touch the rail. Right? It's just there as a protection, as backup. The conical shape actually holds the wheel centered on the rails, right, through there, unless you've got a sharp curve or there's a dip in the track on one side, not on the other, and then it'll jostle back and forth. Then the flange comes in. You'll know when the flange is hitting that rail because it makes that terrible squealing sound. That's the flange hitting the rail as it goes around. You don't usually hear that, right? So usually the flange is not being used actively through there. It's tighter curves is where you'd see that. All right, this is back to terminology. This is what we call a truck. So this whole thing is called a truck underneath the rail car. This is one end of it. All right, up here you can see here's the load limit listed. It's a 202,000 pound. So light. It's only 202,000. But anyway, this is the truck here, and then here's our 2 axles, right? And in a spring loaded, so there's a little bit of dampening through there. So this is a tanker car, obviously, but this will keep the load from jostling too much, right? And you'll see this is a pretty standard setup for a freight car. These this piece over here, right? So this you can see these bearings here on the ends of the axles, right? And then here's a shoe, and it sits in. Look at this. This thing is built like a C almost. It goes around it, right? If you lift this up, these will just fall out. There's nothing holding that bearing into this whole frame over here except gravity. And they don't fall out. Right? How often, it's pretty rare when a freight train catches air going over a hill, right? All right, let's say it never happens. So you don't have to worry about it, right? And this thing ain't going to fall out because it's just held by gravity. But when you have a train wreck, you'll see these sets of wheels with their axles just laying there by themselves a lot of times. And it's because when this thing turned up, they just fell out. There's nothing holding that in. There's nothing under here to hold that in. And it just sets in there by gravity. It's kind of cool. I don't know. I don't know why I think it's cool. I think it's kind of cool. All right, so nowadays rail is continuously welded. They don't have joints in it. So in the old days, they were just bolted together, pieces of rail. They couldn't do welding in the field. This has been probably since the 90s. It really took off through there. So now almost everything is continuously welded. The older track, and especially side tracks, and sometimes in the terminals, right, in the rail yards, some of that's not welded. It probably isn't welded, and then some of that's really crappy looking stuff because they're moving slowly, they don't care. But out on the main line where they want to pick up speed, now they mostly continuously welded. So what's good about that, and what's bad about continuously welded, right? Well, not having joints. What does no joints do for you? Well, no joints is that you don't clickety-clack, clickety-clack, clickety-clack. Every time a wheel goes over that joint, it's not bouncing. Oh, you see the joints in here now, the rail. Can't see the rail there, right? But there's a joint here, even if it's a small joint. Maybe it's only 1/8 of an inch. Maybe it's up to 1/4 inch, right? When a wheel goes across that, that's going to create a dynamic force. You get 286,000 pounds on that thing. Well, not on each wheel, but on the whole rail car. And it click-clacks across that joint, right? That puts a little bit of dynamic force on it. And that's not good, right? Or because you repeat that, how many cars are on a train these days, right? It's usually over 100, and you got 4 wheels per car, and then you've got 100 and some trains a day going by. And super heavyweights. So that wasn't good. So that's one of the big pluses that continuously welded is you don't have that little joint, which can be weak, is a point of weakness, and it doesn't. It'll develop more weakness if you keep continuously loading it like that. All right. So that's one of them. And there's none of that bump and that dynamic stress, right? So the con is that there's no expansion joints, right? When you continuously weld this rail, it is like continuously welded for miles, right? In a number of miles before they'd have another joint, an isolation joint even for that. And this is what happens, right? If it gets really hot, it'll just go and pop out, right? So this flange is holding it in line, and the ties and the sleepers are holding it in line. But if it gets hot enough, all of a sudden it'll just let go, and whoosh, and that's what happens. You have a train wreck, right? Right there. And you can see, like these wheels are no longer attached to their trucks, right? I told you they fell out. So that's what happens. And how do you fix that, right? If you were designing this, you're a materials expert. How are you going to keep this from buckling, right? And so there's a thing they call, well, 2 things. One, you brace it with the sleepers, the ties through that. The other one is that when you weld this rail, you put tension in it. And so they'll list a neutral temperature for this rail, which is when there would be no tension in the rail and no compression in the rail. And that neutral temperature is usually set, it's in the upper 90s to 100 degrees or something, right? That's where they want the neutral temperature to be. So, because in the summer, especially, it depends on where you're at, but if you're in full sun, right, these things are going to heat up. Right, they're dark colored, they're going to absorb the sun energy, and they're going to heat up, right? You don't want this neutral temperature to be 70 degrees because that rail in the summer is going to be in the 90s and maybe 100 degrees, depending on where you're at, right? It is going to buckle if it has that much, if it's that much above its neutral temperature. And so when they weld this, they try to get the neutral temperature. They'll put tension on it, or they'll wait until it is super hot and then weld it. So they prefer to do this in the summer, right? The problem, the other side of that is if it gets super cold, right? That is a lot of tension, and you can't actually crack the rail. I don't know how often that happens, but it can happen, right? I've heard more of this buckling problem, but you can get tension fractures in rail if it gets a lot colder than its neutral temperature. So that's the downsides of the continuously welded. They've worked out most of the kinks in the process, and so this is what Class 1s particularly always are using now is continuously welded rail. And it's pretty cool to watch them do it. They use like a magnesium welding system right there on the track, and it's really bright and smoke flying and everything. It looks like, are they setting the track on fire? Well, they really are. They are welding it right in place. Right. So the other way we keep it from buckling is we secure the rail, and that is with these plates, which tag into the sleeper. And if this was a concrete rail, we would be using they call them a pandrel clip or some kind of a clip, which would have like an anchor bolt inside the concrete tie that would this would come out of and attach to. Well, in wood ones we just use a spike. So here's our spikes, right through there, and so we use this. It's called tie plate. Right, this is a railroad tie. This is a tie plate. Here's the rail. This is from the side view. Whoa, back up. This is from the side view. This is from the top view, right? And you can see we've got a bolt over here, right? And then this one is actually lipped over the flange plate on the rail, right through there. So we pound these in. Some of these actually overhang, like you can see that one. This one's actually just securing the plate to the tie. This one also helps do that. And this one you can see this has been moving. Look at that. All right, when the train goes by, this one has been wiggling. Whoa, and we don't like that, which means this tie is pretty old. Look how beat up it is. Well, these holes are starting to expand and to widen, and you can see how split this is. It's not holding it at all anymore. And so these spikes are starting to wiggle, and so this whole tie plate is shifting one side or the other, right? Maybe it's on a curve, right? That's a pretty bad spot for these. And then you can see the tie plate has a bunch of holes in it, and not all of them are being used. Well, sometimes we use them all, and a lot of times we don't. And we use as many spikes as we need. We don't use extras, right? Because this is also steel and it costs some money for that. The other thing is as these holes wear out or get enlarged, we can move a spike over here and continue using that tie and keep it in service a little bit longer. So this is a spare hole. These are spare holes we can move our spikes over to. Right. And this is an example. This is again from Norfolk Southern. This is how they like to do their ties, right? They have their own standard for this. And if you're on a straight tangent, you just need 2 spikes in that tie plate, right? If you got a 2-degree curve and over, now you're using 3 spikes, 2 on the inside, 1 on the out, right? If you've got a sharper curve, and we'll talk about curve degrees later, now you're using 4 spikes and you're sticking some on the far sides. And then if you've got a really, really sharp curve, 13, right, now you're using 1, 2, 3, 4, 5 spikes in it. So the tie plate is kind of universal, and then we just stick in as many spikes as we need for what we're doing. On a straight track tangent, 2 spikes is enough on each tie plate. Yeah, kind of interesting, right? So that's I guess that's why the difference is what's the lateral force. I'm going to answer my own question. It's the lateral forces, right? As this degree of curve goes up, you're getting more shoving, pushing to the side, one side or the other, so you're using more ties from that. All right. So we'll end there this time. Next time we'll pick up and talk more about track in railroads.